Welcome everyone, my name is NUSRATINA SYAFIQAH, and let me introduce you to the tournament ranking system, which is designed to manage player rankings in a tournament using a binary heap. This system ensures that players are ranked based on their scores. A binary heap is utilized to enable efficient insertion, deletion, and retrieval of player rankings. The heap structure ensures that the highest scoring player is always at the top, allowing us to efficiently identify and update rankings as scores change. By leveraging this approach, the system maintains order and stability even as players join, leave, or update their scores. Next, I will explain the key features of our binary heap-based tournament ranking system and how these operations work to manage player rankings efficiently. The first feature is register player. This allows us to add new players to the tournament. When a new player registers, their name and initial score, usually 0, are inserted into the binary heap. The heap automatically ensures that the player is positioned correctly based on their score. For example, if player A joins with a score of 0, they will be placed at the appropriate position within the heap. This operation ensures that the rankings remain valid as new players are added. The second feature is submit score. This is used to update a player's score after they have completed a match. When a player's score changes, the binary heap automatically rebalances itself to reflect the new rankings. For instance, if player A's score increases from 0 to 50, the heap will adjust player A's position so they move higher in the rankings. This operation is efficient as it maintains the heap property with minimal computational effort. The third feature is get top player. This operation retrieves the player with the highest score. In our binary heap, the player with the highest score is always stored at the root node. This means we can instantly identify the top player without needing to search through all the data. For example, if player C is the highest scorer, this operation will immediately return player C. The fourth feature is get player rank. This operation calculates a specific player's rank within the tournament. Using the heap, we can traverse the structure or use additional tracking mechanism to identify the player's position in the rankings. For instance, if players D's score places them third overall, this feature will return their rank as 3. This is a helpful feature for players to know where they stand in real time. The final feature is remove player. This operation removes a player from the tournament. For example, if a player decides to withdraw or is disqualified, this feature ensures that they are removed from the rankings. The binary heap handles this efficiently by replacing the removed player with the last player in the heap and rebalancing the structure using a process called heapify down. For example, if player B leaves, the heap adjusts itself to maintain the correct order.
Hi everyone, my name is MUNIRAH binti MUNIR. So today I will talk about how our tournament ranking system works behind the scene. So basically we use something called a binary heap to organize and store player rankings. So there are two main things we do with NQ and DQ. So NQ is which is adding a new data, while DQ is removing the data. So both of these are super quick because the binary heap works in O log n. Okay, in simpler terms, it keeps everything running smoothly even if we have a ton of players. Okay, so I will talking about through a dynamic example of how a tournament ranking system operates using a compact array in binary heap. You will notice how numbers are NQ, compare, and swap with I also include the movement illustration at the below, so that will explain each steps to make the process clear. So I will start with number 1 by inserting the number 19 into the compact array. So it's added at the back, and since there's no comparison needed yet. Okay, next, the number 2 is insert since number 2 is smaller than 19. So a swap occurs. You will notice the arrow indicating the movement of 2 as it swaps position with 19. So this movement ensures the structure maintains its order. Alright, so number 3. Number 3, after the swap, the array is now valid. Okay, now valid, and 19 is successfully inserted in its correct position. And then the number 1 is added at the back. There are no invalid nodes, so 1 is placed without any movement. Okay, step number 4. Step number 4. Now I insert the number 90, which is invalid nodes appear in the red, and I will need to make adjustment. So you will watch how the numbers move in the upcoming step to fix this in the movement illustration. Step number 5. First 7 is smaller than 90, so a swap occurs. The movement of 7 to the top and 19 downwards is shown with the arrows. So So illustrating how the structure begins to reorganize itself. Step number 6. Next, 26 is compared with 90 and another swap takes place. Again, you can see the movement as 26 move up and 90 adjusts its position. The invalid nodes are clear step by step. So step number 7, finally the corrections are complete and 90 is successfully insert. The movement illustrates how the system then dynamically rearrange elements to maintain order. Step number 8. Now the NQ operation continues with other numbers. The movement illustration, you will see ensure that each insertion dynamically adjusts the array to represent the ranking accurately. Alright, so now we will move on to the DQ operation in our tournament ranking system. This is the process where we remove the maximum item stored in the root and reorganize the structure to maintain its properties. Alright, so we see step by step how to observe the movement. So I also include the movement illustration at the below. Okay, step number 1. First, the root of the compact array stores the maximum item. In this example, the root contains 90. This is where the DQ process begins. Okay, next, we remove the root item, which is number 90. So the system prepares to reorganize the structure by replacing the root with the last leaf. Okay, step number 3. To fill the gap left by the removed root, so we replace it with the last leaf, which is number 2. At this stage, the structure is temporarily invalid, and we will notice invalid nodes, which is in the color red. Okay, so number 4, step number 4, the number 2 becomes the new root. However, invalid the nodes it remains. So this system begins swapping operations to correct the structure. You also can watch the movement illustration in the below. So step number 5. Okay, in this step, number 2 is compared with its child 35 since number 2 is smaller. So we will swap them. The movement of number 2 down and 35 up is shown with arrows illustrating how the structure begins to restore order. Okay, so step number 4. The number 2 is compared with 26. So the number 2 is smaller, so another swap occurs. The movement of number 2 down and 26 up is clearly depicted in the illustration. So with this, the invalid nodes are resolved. The final step, which is step number 7, the DQ operation is complete. The system has successfully returned the maximum item, which is 90. The structure is now valid and ready for the next operations. So that's how the DQ operation and NQ operation works in our tournament ranking system.
At this part, I will walk you through a Java code method called NQ. So what does the NQ method do? Let me answer for that question. The NQ method is to add an element to a priority queue, which is implemented as a binary heap. A binary heap is a data structure that ensures the smallest elements, which is in the case of a min heap, is always at the root. This method adds a new element to the heap while maintaining the heap ordering property, which ensures that every parent node has a key less than or equal to its children. So let's dive into the code and understand how it works. So let's walk through this code. Here's the code for the NQ method. The method takes two parameters, which is the first is value, the value that data we want to store, and then the second is the priority of the data, which determines its position in the heap. So the first important step of this code is we have to increase the size of the heap, because we keep track of the number of the element in our data structure. So by then we know if we have to add a new element if necessary. Then the that word is a reference to the array holding in the heap data. Whole words represent the position where the new element will be inserted in start at the end of the heap. Next, we calculate the parent of the whole, where we will insert the new element in a binary heap. The parent of a node at position I is at position I over 2. We also use the bitewise shift operator greater than symbol for efficient division. We then retrieve the key of the parent node using pred key, which we'll use to compare prioritize. The method is defined as public void NQ, which v value and k key. The heart of the method is these while loops, which restore the heap property by bubbling up the new element if necessary. We compare the parent key, which is the pred key, with the new key. If the parent's key is greater, the parents violate the heap property. In that case, we move the parent down into the hole. The hole move up to the parent's position, and we repeat the process with the new parents. This process continues until we find the correct position for the new element. Finally, once the correct position for the new element is found, which is when no parent's key is greater than our new key, we place the key and value into the hole at this point. The heap property is restored and the new element is correctly placed.
Assalamualaikum warahmatullahi wabarakatuh. My name is HANIF and HAZLAN. So today I will present about the tournament ranking system for the key operation and then the interface use and class in the coding. So the application is a tournament ranking system using the binary heap class, which function as a priority queue. It uses an internal array to maintain its structure and relies on the system.i comparable interface for comparing keys to keep the heap property intact. So that's for class and interface. The key operation in the binary heap, the first one is NQ. So this operation adds a new player and their score to the heap. So the new player is initially placed at the end of the heap. The system then compares the new player score with their parent score and swaps position if necessary, repeating this until the heap property is restored. So this process ensures the highest priority players remains at the root. So the second one is DQ. So this operation for remove and return the top ranked player. So the root element which is high property is removed. So the last player in the heap is moved to the root. The system compares the new root scores with its children's score, swapping as needed until the heap property is restored. So the third one is clear. So this key operation for clear all element from the heap, resetting it to an empty state. So the fourth one, which is the last one for key operation, is count. So this key operation function is return the total number of players currently in the heap. So these operations are highly efficient with a time complexity of O log n, making them scalable for managing large tournaments.
To wrap up, let's summarize the key features and benefits of using binary heap for our tournament ranking system. The binary heap enables fast insertion and retrieval of scores, ensuring that rankings are consistently updated and accurate. The primary operations used are NQ, which is for inserting a player or updating the score, DQ for removing a player or identifying the top scorer. Both of these operations have a time complexity of 0 log n, making the system highly efficient when even managing a large number of players. This means the system remains quick and responsive, regardless of skills, which is crucial for real-time tournament applications. In conclusion, the binary heap proves to be an excellent choice for managing and prioritizing data efficiently, especially in systems like this tournament ranking system. Thank you for your attention.